So let me start. I will talk about the existence of designs. As I learned over lunch, the word design came originally from French, but certainly in mathematics it was used in English, and there was a hard time finding the translation of the mathematical term design back to French. But I think eventually the choice was to use the name design. In any case, I'll speak in English. I will talk about the existence of designs after the work of Peter Keevash. So let me start by telling you what designs are. Okay, so a set, we are talking about collection of sets. We start from a set with n elements, x, and we look at collections of q subsets, sets of size q from x, and it is designed with parameter n, q, r, and lambda. So n is the size of the ground set, q is the size of the subsets, which are also called blocks of the designs, and r is an integer which gives the condition. The condition is that every r subset of x belongs to exactly lambda elements of S. So we have collections of sets of size q. Let's give an example. Say q is 11. So we have sets of size 11 from, say, a set of size 100. And every subset of size 5 belong to precisely one such set. So this is a design. So as you can see, this is a very regular object that when we look, and a special case is the case where lambda is equal to 1. So in this case, every set of size r belongs to a single set of size q. And then a design is called a Steiner system. And then we don't need and then the parameters are n, q, and r. And the question if Steiner systems of given parameters exist, they go back to works from the 19th century by Plücker, perhaps mainly Kirkman and Steiner. And until 18 months ago, there was not a single example of a Steiner system for r greater than 5. So so we didn't have any single example of a Steiner system until for r equal to 5. So let's just practice this notion for some simple cases. Let's take the case that q is 2 and r is 1. If q is 2 and r is 1, we are talking about collections of pairs, right? Collection of pairs, and we want that every element from x is included in lambda pairs. So this structure is called, this is a graph. Collection of pairs is a graph, and this is what's called the regular graph. We know many regular graphs. If lambda equal 1, then this regular graph is just collection of edges, pairwise disjoint edges. If lambda is larger, if lambda is 2, then this graph is a collection of cycles whose union is the entire set of n elements. And if lambda is larger, then this is a 3 regular graph, so those are more interesting combinatorial objects. I think the story starts to become interesting and or even more interesting when q is 3. So here you see a famous design where the set, we have a set of size 7. These are the 7 points drawn here. And we have 7 sets of size 3. And these 7 sets are, this is the Fano plane that most of you, I suppose, recognize. The 7 sets are represented by the 6 straight line and 1 circular line. And they are the 7 lines of the finite projective space over a field with 2 elements. So you see here you have 7 triples, and every pairs of elements belong to a single triple. So this is a design. And in general, finite projective spaces are special types of design. And this particular design, if the sets are of size 3, then this is called the Steiner triple systems. And both Steiner and Kirkman were interested in the existence of triple systems. Okay, now when we have a design, then we cannot prescribe the parameters Q. So let me just write here the parameters. So we have N, Q, R, and lambda. We cannot prescribe the parameter N, Q, R, and lambda completely arbitrary. There are some divisibility conditions, and here is we will come back to them. But here is a basic property that must be satisfied, and this is that Q minus I choose R minus I should divide lambda times N minus I choose R minus I for every I between 0 and R minus 1. So this, and to see why this divisibility condition holds, you have to fix some I subset and consider the blocks in the design containing this I subset. So if you fix an I subset, this I subset will be included in Q minus I choose R minus I sets of size Q, and well, let me not try to prove it. But in any case, we will come to some simpler argument of this kind. In particular, for example, if you have a 3-regular graph, then the number n should be even. And this is a condition of this same nature. So these are very simple arithmetic conditions for the existence of designs. And people ask if there are, people knew that for some cases these conditions are not sufficient, but it was conjectured that perhaps when n is large enough, these conditions are sufficient. And as I said, for large n, for most parameters, there was not a single example, but nevertheless, this was a conjecture that I think most people in the field thought is quite plausible, and this is now a theorem. And here what it says, for fixed Q, R, and lambda, there exists some number n0 of Q, R of lambda, that if n is larger than n0 than this number, and the divisibility conditions hold, then a design with parameter n, Q, R, and lambda exists. In other words, there's only finite number of exceptions of the divisibility condition, and apart from these exceptions, designs always exist. So this theorem was quite a surprise because we hardly had any examples, and then suddenly Keevash came with his surprising proof, and now we know that these things exist whenever it's possible, except for a finite number of exceptions. And let me tell you briefly what are the 3 ingredients in the proof, and the lecture will elaborate on them, but I think I should mention the ideas already now. So the first idea is what can be called the greedy random method. So it is a special, it's part of a big idea in discrete mathematics to use randomization, to use a probabilistic argument to prove the existence of certain object. But the greedy random method is a particular method that was developed to prove the existence of things that direct probabilistic arguments are too weak to prove. And here the method is intertwined with other ingredients. First, it is used to get an approximate construction for the design, and then it is used to patch the approximate construction to get an exact construction. And one can fairly say that Keevash proof is spoken in the language of the greedy random method. So most of the proof use and reuse various ways this method. Then another ingredient of the proof is a certain auxiliary algebraic construction, also that involves some randomization, which is sort of a crucial apparatus for the ability to correct and approximate the composition toward an exact decomposition. So you build something approximate, and then you need some tool, some structure to correct it. And for that, Keevash described a certain algebraic construction that I will mention, at least in a special case, what it is. And then a third ingredient is a certain integral relaxation of the notion of design. So as often is the case in many areas of mathematics, also here, when you have a question, you want a generalized notion of solution or a weak notion of solution. And here, when you think about designs as solving integral equations where the variables should get variables 0 and 1, you can relax it and ask what happened if the variables get integer values. And this was considered in the 70s. It's not very difficult. And somehow the structure of the octahedron plays a role there. And again, we will see it in more details later. And this is the third ingredient of the proof. Okay, so the first part I want to talk is about regularity, symmetry, and randomness. Those are three topics or three concepts which are quite important for this discussion. So designs are very regular objects. Regular objects roughly speaks to objects which locally look the same. So you can think about a manifold as a regular object, and you can think about Lie groups as symmetric objects. So sometimes regularity comes from a group action. And in this case, you can get design by looking at a transitive group. And here is a very simple proposition. If you have a T-transitive permutation group, so a permutation group is T-transitive if for every two sets of size T, there is a group element that map one set to the other. So if you have a T-transitive permutation group, then the orbit of set of size K or of size Q is a block design. So every set of size R belongs to the same number of blocks. So this is a way to get a block design from highly transitive groups. Unfortunately, there are not many highly transitive groups. There is a famous consequence of the classification of finite simple group, which asserts that a T-transitive permutation group for T greater than 5 are only AN and SN. So they don't give any interesting designs. They just give the entire collection of sets. So, and certainly not of Steiner systems. So we do get interesting designs from highly transitive groups, and we'll come back to the connection later, but this is limited to the parameter 5. We cannot get anything, at least not directly, below 5. It's still interesting if there are some more sophisticated way to get designs from groups in some other way for some other parameters. Okay, now we move to the probabilistic method. So as I said, one of the most important methods in modern combinatorics is in order to prove the existence of objects of some kind satisfying some property, we consider some probability distribution on all objects, and we show that the probability for having this property is non-zero. And this method is very powerful. There are many cases where we cannot substitute it by any other method for proving the existence of certain combinatorial objects and also various geometric objects. And this became quite a main problem. So here is a challenge for you. If you, for example, suppose we want to prove that there is an injective map from a set A of n elements to a set B with m elements. So I'm sure, so if you want to use the probabilistic method to prove this statement, this is quite easy if m is bigger than n squared. Because by the birthday paradox, if you take a random map from a set of n elements to a set of n square elements, then it will be injective. But as long as we have less than, so as long as we have more than square root of 365 people in the room, it's likely that there will be two with the same birthday. So this method is fairly powerless when m is smaller than n squared. There are more a deeper probabilistic method, in this case application of what's known as the Lovász local lemma, which allow you to prove that there is an injective map when m is bigger than 10n. Now, okay, so the challenge for you is to try to prove that when m is equal to n, to find a bona fide probabilistic proof that there is indeed an injective map. Of course, it's not, this is not an entirely well-defined equation, but when you send me the probabilistic proof, I will be able to test if this is a genuine probabilistic proof by implementing your idea on some open problem where the existence of this object is not. Okay, so another important idea in this field is the notion of quasi-randomness. So quasi-randomness refers to structure which behave similarly to random structure, but they are defined using deterministic conditions. So for example, here is a definition for graphs. A sequence of graph Gn, so usually it's an asymptotic notion which apply to structure when n goes to infinity. A sequence of graphs is quasi-random if the number of induced Force cycles, so you look at the Force cycles, so you look inside the graph at 4 vertices where the edges on these 4 vertices are Force cycles. They look like this. These guys do not belong. And it turns out, of course, if you have a random graph, you can compute what is the expected number of Force cycles. The expected number of Force cycles is 1 over 64 times the number of 4 tuples. Because if you take a 4 tuples, the probability that these 4 edges will be presented and these 2 edges will not be presented is 1 over 64. But it turns out, and this was a series, it was developed by Andrew Thomason and also by Fen Chang, Ron Gam, and Richard Wilson. And Rick Wilson is quite a hero in several developments discussed here, that this particular property, the number of Force cycles, capture a lot of the property of a graph to be a random graph. And there are various other examples of the notion of quasi-randomness. For example, primes have a lot of quasi-random properties as subset of the integers. Sets with diminishing Fourier coefficients have a lot of pleasant quasi-random properties, and these are related to the other example. Expander graph, those of you who heard about expander graphs, so they are similar to the example I mentioned before, but they are graphs with regular graph with small degrees, and expander graphs are example of graphs which are defined using deterministic notion, but have properties of, in various respects, as if they were random. So quasi-randomness plays a crucial role in various development, both in combinatorics and outside combinatorics, and also in this result. So essentially, I will now describe, in order to, the machinery of Keevash proof, and this also applies to some earlier results about approximate design, is essentially to vastly generalize the theorem as to talk about the composition of quasi-regular objects. And let me describe now the language where the general results. So after I will present you the general results that Keevash proof, I will zoom back to a very special case of the general result which allow best to demonstrate the ideas. And now we have to talk about a hypergraph. A hypergraph is a ground set, which are called vertices, and a set of edges, which are subsets of the set of the vertices. And if every edge has size r, then we say that G is a R-uniform hypergraph. So when R is 2, then a hypergraph is simply a graph. So if we have a subset of vertices, then the link of these vertices is, I'm sorry, here there is a minus missing, is the R minus the size of I uniform hypergraph, where you take all the edges of the hypergraph which contain I and delete I from them. Or in other ways, you look at all the subsets of the vertices except I, so that when you add I, you get an edge of the hypergraph. So this is very similar to the notion of a link that we are familiar with. And now when we have a hypergraph, we want to decompose the edges to small hypergraphs which are isomorphic to a given hypergraph H. So the questions about designs can be asked in greater generality as questions about H decomposition, the composition of a hypergraph to small pieces so that every piece is isomorphic to a given hypergraph H. And now we denote by KRQ is the complete R-uniform hypergraph on Q vertices. So this is a hypergraph where you have all the edges, all the R subsets from a set of size Q. And looking at it in this way, a Steiner system with parameter N, Q, and R is equivalent to a decomposition of the complete hypergraph, R-uniform hypergraph on N vertices, to many copies of the complete R-uniform hypergraph on Q vertices. So this is simply a translation of the notion to this language. But now we will, after we have this translation, we again can talk about two notions. The first is, in order to have a divisibility, we need some, in order to have the composition, we need some divisibility properties. For example, the obvious property, if we want to decompose a big hypergraph to small hypergraph of size H, we need that the number of edges in the big hypergraph divide, or the number of edges in H divides the number of edges in the big hypergraph. So this is to make the decomposition at least arithmetically possible. And we also need the same thing also for links. So here again we have a similar condition. If we have an R-uniform hypergraph, we will say that we will call it KQR divisible if Q minus I choose R minus I divides G of I, the link of every set I of size I. So this is the necessary divisibility condition for such a decomposition. Now the second condition is a quasi-randomness condition. And let me tell you in words what this condition says. We look at the R-uniform hypergraph, and to say that it's quasi-random, and here the technical name is CH typical, it means that if we take the intersection of several links of sets of size R minus 1, then this intersection, the size of this intersection behave up to a small error, which is here denoted by C, like it would have behaved for a random hypergraph. So this is the technical condition. Again, I don't insist that you will digest this condition, because we will move to a special case where things will be even clearer. But this is the quasi-randomness assumption. And now Keevash's theorem, in this generality, actually he even goes further to a greater generality. But Keevash's theorem, let me say it in words, says that if we have a hypergraph, if this hypergraph is typical or quasi-random, and if it satisfies the arithmetic divisibility problem, then it can be decomposed into complete hypergraph of size, complete R-uniform hypergraphs on Q vertices. So if it satisfies the divisibility condition, and if it is typical, if it behaves like a random hypergraph, then it can be decomposed. And of course, this implies the original result, because when n is large, the complete hypergraph will be typical. So this will satisfy, this will imply the result about designs.
Question.
Yes.
The double lessness, do you mean just bigger, or do you mean something more?
This means that it's sufficiently smaller. It's smaller than a constant. So okay. Everything can be proportional, but you can tune the constants. So you need this. You need this constant.
That C is much larger than 1 over n.
No, it's just larger by any prescribed constant. By any prescribed constant, or you can make this constant. Okay, so I want to impress you by Keevash's general theorem, but then I will tell the special case that will be. Okay, now, although designs were not known 18 months ago to exist at all, with the new technique we can actually tell a fairly good estimate about the number of designs. And another theorem, and again, this theorem also applied to the greater generality of the previous theorem, but I'll just mention it here. The number of Steiner systems with parameters n, q, and r, when n satisfies the divisibility condition, satisfy the following relation. The log of this number is 1 plus little of 1, q choose r to the power minus 1, n choose r times q minus r times log n. So
R are fixed, right?
yeah, here, this is very important. Here, q and r are fixed and n go to infinity. And all this work is for the case that q and r are fixed and n go to infinity. It's also interesting to understand the regime where both n, q, and r simultaneously go to infinity, and this is this is unrelated to this work. I may mention a few words about it, but here q and r are fixed, n go to infinity, and this gives you the asymptotic of the logarithm of the number of designs. And if you want to understand where this asymptotic comes from, it comes from the very naive probabilistic argument, which is a false argument, which says that the probability that a set of size R belong to a unique set of size Q, or the number of sets, if you take the right number of sets of size Q, this has a Poisson distribution. So if you choose the number of blocks to be the number of blocks you expect from a design, then the probability that all the regularity condition will hold will be 1 over e to the power, which is the number of sets of size R. So this is, of course, a false argument, because there is no independence, and it's even completely blind to the divisibility condition, but it gives the right asymptotic for the logarithmic of the number of designs. You can still hope for more and for some good asymptotics for the actual number of designs. So, but this is pretty good as it is. Okay, let me say a little bit. So now now that I presented the Keevash result, let me say a little bit about the history of the theory of designs. So I think it's fair to start with the earliest general existence result, which was given by Kirkman in 1847. And in this paper, he constructed Steiner triple systems for every n which is 1 or 3 modulo 6. So if you look at the condition for triple systems, we have triple system, we have collection of triples from an n-element set, so that every pair is included in one triple. This can happen only if n is 1 or is 1 or 3 modulo 6. And Kirkman wrote a paper where he actually proved that for every n, which is 1 or 6 modulo 6, this object he didn't call them Steiner triple systems for reasons that you will see immediately, but in any case, he proved that they exist. And there is some prehistory which go back to Plücker, and Plücker didn't study them systematically, but he encountered this structure in his rock on plane cubic curves. And then there were some questions. So you see that this objects, they also have some recreational appeal. Indeed, there was in some journal, which is called the Ladies and Gentlemen Diary, which we will meet again. There was a question in 1844 about the number of designs. Now, of course, the designs are related to things that people were excited even earlier, like the Latin square and Greco-Latin square. So this is something that people were excited about from ancient times. And curiously, few years after Kirkman, Steiner, a well-known geometer, also he was not aware of Kirkman's work, and he posed the question about the existence of designs. He didn't prove any general theorem, but he asked it as a question. And then Rice solved the question for the case of 3, just reproved what Kirkman do about 10 or 15 years later, 12 years later. But perhaps the question which is most famous at the beginning of the story's design comes from another contribution of Kirkman. So this was not his serious mathematical paper, but another puzzle he posed in, again, the same journal, Ladies and Gentlemen Diary. And this is the question about 15 young ladies. And the question is the following. There are 15 schoolgirls who take their daily walks in rows of 3s. It is required to arrange them daily for a week so that no 2 schoolgirls will walk in the same row more than once. So every day there are, okay, let me just, we can look at the picture in the next slide. So every day the girls there are 15 pairs of girls who are in the same row. And if there are 7 days, there are altogether 105 pairs of girls, and this is precisely the number of 15 choose 2. So arithmetically, it's possible perhaps to divide. The divisibility condition holds, but the question, can you have such a design? And this was a question that Kirkman asked, and several people offer, there were about 6 or 7 solutions, some of them by well-known mathematicians like Kelly, some of them by layperson. The original solutions looked fairly ad hoc, but few years afterwards, there were sort of more conceptual ideas toward the solution. So this problem drew quite some interest. And you can ask this question for any n, which is 3 mod 6. So this is slightly more, this is a design with some extra structure, because you want that the blocks of the design can be divided. You want into what's called the matching. If you ask a Kirkman original question, you can ask it for every n which is 3 modulo 6. And surprisingly, this particular case, it was not until about 100 years later that a solution was published for all n which are 3 modulo 6. One solution was by a school teacher from Mongolia, and one solution was by a very central researcher, Ray Chondry and Wilson. And Sylvester was also interested in this problem. He had some ideas about the history. But in any case, he asked another question. He asked, can you find 13 different solutions for the Kirkman problem, which altogether combined will give all the 15 choose 3 triples? So if you look at the arithmetic, you see this is arithmetically it's possible. Sylvester asked, If this is possible in general, this can be called Sylvester designs. There are even more general objects. And this was settled by Dennis Stone. He found such a decomposition. And I think, as far as I know, this is not known in general. Now, in the first half of the 20th century, combinatorial design played some role in statistics, in experimental design in statistics. The famous statistician Roland Fisher was quite interested in design. He had some important results about them. I may mention a little bit later. And it was also important in group theory and very closely related to error correcting code. So this is another mathematical discipline that was developed for very important real-life application. So, for example, the story about 5 design and the 5 and 4 transitive groups is quite interesting. The only 4 transitive groups, apart from AN and SN, are the so-called Matthew groups. So Matthew discovered them around 1860, 1870. And when he described these groups, it was still a little bit controversial if these groups exist or not. So he described them in terms of relations, generators and relations, and by some other means. And there were papers claiming that these proofs do not exist. Actually, these papers were incorrect eventually. And in 1938, Witt described two of the Matthew groups, and the other can also be derived, as automorphism groups of some combinatorial design, which is now called the Witt design. So this is a Steiner system of parameter 24, 8, and 5, and the automorphism group of this Steiner system give you the Matthew group. And this is a very definite existent proof for this important sporadic group. And then about 10 years later, Golay used similar construction based on Matthew groups, and we designed to find very important error correcting codes, which are heavily used in transmission for the purpose of, I think the Voyager mission was reliable, the transmission there, the telecommunication there was based on this. So now I want to describe a landmark in the theory which happened in the 70s and 80s. In 1972 up to 75, Rick Wilson proved the existence of designs. He proved the existence conjecture for designs for the parameter, for the parameter R equal 2. So systems of sets where every pair of elements are included in Q elements. Again, Q is a fixed number, n go to infinity. There are some divisibility conditions, at this time only 2 divisibility conditions, and Wilson proved that apart from a finite number of exceptions, for every fixed Q, these designs exist. So this was a very beautiful breakthrough. And in 1987, Teirlink proved that design exists if you allow lambda to be large. So lambda is a number of times every set of size R is included in a set of size Q. If you allow lambda to be large, then you can build this design. Lambda can be very large depending on K and R, but it's independent from N. And this is a very beautiful result. It is based on sort of classical ideas that people use to build designs, very complicated and ingenious combinatorial inductive arguments moving from one set of parameters to the others, from one end to the other, and eventually it leads to these structures. This is a very beautiful piece of work, and this would. Okay, another work which I already hinted is also by Wilson and also by Grever and Urquhart. They consider the design is a solution for certain equation. You want coefficient, you want variables for every set of size Q, and you want that if you sum all these variables for all the sets which contain a set of size R, you get 1. And the initial constraint on this variable is that the values will be 0, 1 values. And they ask what happens if instead of talking about 0, 1 values, we talk about integer values. So this is some sort of designs, but it's like virtual design if you want to adopt the representation theory language. You allow to have sets with positive and negative integer coefficient, and then they show that the divisibility condition, which is still necessary, is also sufficient without any exception for the existence of these designs. And this is very nice. And something which is used is this structure, which you may, well, I'll try to draw an octahedron as nice as I can. So the octahedron, so this is just for the case of triples. The octahedron has the nice, it's a collection of triples. And if you put signs plus and minus alternating on adjacent triangles, then the total contribution of all the edges is 0. So in some sense, this looks like you can think about it as like the boundary operator from usual simplicial homology, except you don't have any signs. In the boundary operator, the matrices have some signs. Here, this is a signless boundary operator. So this is not so useful for topological purposes as a simplicial homology, but this is still quite a useful object in combinatorics. And you see that if you take the alternating sum of all these triangles, then the contribution on every edge will be 0. So this means that for this type of construction, you can use this as something that you can always add and subtract this octahedron. This is quite a nice. Okay, so now I'll move to the third part, which is the greedy random method. So let me go quickly. So the probabilistic heuristic, I referred to it a little before. Let me just do it very quickly. Suppose you look at the problem very naively and you ask, what is the probability that a collection of sets of size q, which has the right number, n choose r divided by q choose r, what is the probability that this collection will be a design? And as I said, one way to go about it is to see that the probability that a set of size r will be included in a unique set of size q is roughly 1 over e. So this gives you some estimate, which is completely nonsense, but it's still useful in some purposes. And I will refer to it as the probabilistic heuristic. Now, you can do, okay, let me just say, you can use the probabilistic method and ask how many sets of size r can I have so that every set of size q, how many sets of size q can I have so that every set of size r will be included in at most one set. And if you use the naive probabilistic argument, you will get something which is quite smaller than b by some polynomial factor in n, but so you will get some result. And this is Erdös and Hanani, they ask perhaps if we cannot prove the existence of designs, maybe we can prove that approximate designs exist. Maybe we can find a collection of sets of size q so that every set of size r is included in one of them, except perhaps a small fraction of the sets. So there are several variants. Either you want that every set of size r is included in at most one, and most sets are included in precisely one, or the other way around. Every set of size r is included in at least one, and most of them are included in at most one. So this was a conjecture, and then Rödl proved this conjecture. And this is a theorem from 1985. For every fixed q and r, there exists nearly Steiner system of parameter n, q, and r. Namely, a system of the right number times 1 plus little o of 1, so that every set of size r is included in at most one block in the system. What is the idea of the proof? The idea of the proof, this is it's now known under the name of Rödl-Nibel. So this is the idea of using what I call the greedy random method. This is a method which I think was introduced in some different version by Aitai, Komlosh, and Semeredy to study Ramsey numbers. And then Rödl was able to implement it or to develop it in the way needed for the existence of approximate design. And the idea is, what you do is you choose at random a certain number of sets of size q, so that these sets cover the sets of size r in a very good way. So every set of size r is covered once, and you show that with high probability, the sets of size r which are covered, they have quasi-random behavior. The sets of size r which are not covered also have a quasi-random behavior. And also the set of size q which are chosen have a quasi-random behavior. And then, using this quasi-randomness, you repeat this process. And again, this time you don't start from the whole collection of q sets, but only from the remaining q sets. But you use the quasi-randomness that you proved hold with high probability in the first step, and you repeat this process. So this is the sort of the greedy random method. You can think about it as a way to use randomness for optimization. So you can think about it as a general paradigm to use randomness for optimization where you need to find very rare objects. And shortly after Rödl found his, I should mention here, I will just be brief, but then people start looking at the Rödl proof and saw that this proof applies, you can abstractize immensely the context where this method is applicable. And this was first suggested in a paper by Rödl and by Frankel and Rödl, and then there was a definite result by Pippinger and Spencer, and they show that you need very little from the initial combinatorial problem to make this Rödl-Nibel apply. And indeed, as I said, so one can think about the Rödl-Nibel as a sort of an analog to the so-called I forgot the name. So there was a famous Romanian gymnastist who is famous for the flip she introduced. Olga, what? Do you remember? What? Korbut, yeah. So the Korbut flip is a oh yeah, she was Russian, yeah. Korbut flip is a way to do a backward salt on the balance bar. And this was something she introduced in 1972. It was very difficult. Then slowly, after 4 years, almost any gymnast do it. And then I think Comaneci came, and she could do many of those things simultaneously. So what happened here is similar, that there was this Rödl flip with some coaching of Aitai, Komlosh, Semeredy, and he do something which looked completely impossible. And then people start to understand what is the machinery and start to apply it. And now a large part of Keevash's work is to virtuously develop this tool of the quasi-random method and to apply it in very, very general situation. But there is some extra thing he need to do, and now let me describe Keevash proof. So in order to describe Keevash proof, I will go to a very special case. And the very special case is the case of covering by triangles or covering by triples. So now we will, we will consider the question, you have a graph, and you want to cover the edges by edge disjoint triangles. So when we think about the complete graph, sorry, I'm losing my voice slowly, but I hope. So when we think about the complete graph, then this is precisely the question of Steiner triple systems that Kirkman solved even before Steiner posed the question 150 years ago. But when we consider about quasi-random graph, this is already an open question. And this is a special case of what Keevash do. It is easier than the general case, but it's easy to... So we have a graph G, and we want to decompose it to triangles. Okay, so first of all, we have some divisibility conditions, what they are. So here it's easy to say what they are. First of all, we need that the number of edges of G is divisible by 3. And the other thing we need that the degree of every vertex is divisible by 2. Because if we have triangles, we look at the length of a vertex, every triangle occupies 2 edges. So the degree of a vertex is divisible by 2, and the number of edges is divisible by 3. And we will call a graph with these properties trivisible. So this is the analog of the divisibility condition, which are more complicated in the previous theorems. And now a graph is typical if so a graph is CT typical if when we look at the intersection of neighbors of vertices and we look at most k vertices, then the number of vertices in this intersection is between 1 minus c times the density of the graph to the power of this size x. So it's almost determined. So again, this is a quasi-random. Let me see if I can. Okay, so this is a quasi-random property. And the Keevash result is every time, if you have a C, 16 typical graph of density D, and then you can, then for every density, there is some constant C, this error margin. So if you have a graph which is trivisible, and it's typical, it's quasi-random, then you can decompose it to triangles. So this theorem is already extremely beyond what was known even for this very special case of decomposition into triangles. And this is a good way to demonstrate. Okay, so I will, what I will do, I will tell you the infrastructure that Keevash used, and then I will quickly tell you how we put it together. So here is, let me see what I can do. Maybe I can move it. Okay. So the first thing he do is he consider a sort of auxiliary class of triangles. So he look at so we have this graph. So this is a graph G. Now we think about G, the vertices of G. We think about them as sitting inside a field with 2 to the a elements, and so here there are n vertices. So n is between 2 to the n minus 2 and 2 to the n minus 1. So this field has at least n additional points. So this is the field. Inside this field, so he think about some random map from the vertices of G to non-zero elements of this field. Now, in this field, you think about all the triangles with sum up to 0. So if you have 3 elements in the field with sum up to 0, then okay, so sometimes they don't belong to G. Sometimes they do belong to G, but the vertices do belong to G. But it's not clear that the edges are edges of the graph. So there is some probability, which is the density of the graph to the cube times some constant between quarter and half, that such a triangle will be in the graph. And he looked at all the triangles which correspond to triples of elements in the field which sum up to 0, which belong to this graph. So this can be a collection of triangles, which is a small collection of triangles inside our graph. And he considered all the edges of all these triangles. And all these edges of all these triangles, again, this is a small number of edges compared to all the edges of the. Okay, so this is one thing needed for the proof. Another thing needed for the proof is the following idea: is that if we have a triangle decomposition, and we want to find a new triangle decomposition which is not using a specific edge E. So this edge E belongs to some triangle, and we want to find a new triangle, a new decomposition which covers all the edges of the previous decomposition except E. Then there is some way to do it, and the way to do it is to consider 2 such triangles and embed them into octahedron. So this is the structure I mentioned before. And then by juggling with the signs of the triangles, we can move from one decomposition to another where there is precisely one edge which was covered before and not covered now. So this is, of course, to implement this operation, we need that all the relevant edges will be present in the graph. But since the graph is quasi-random, every property of this kind holds with positive probability, so we will have many such octahedra to our disposal. So this is a second idea which is needed. And then there is another construction which Keevash used. Again, it's a simplified way in this particular special case. This is using this template of triangles. He considered a large subgraph of our graph. This is a graph with 24 vertices, and he considered all the 8 cube triangles, which consist of taking one vertex from each of a group of 8. And when you have these triangles, he can use the field F star to build 2 decompositions. One decomposition have triangles only in the template, only among these very special triangles that you use here, and another composition have only triangles which are not in the template. And by juggling between these 2 decomposition, this plays a crucial role in the construction. And again, using quasi-randomness, he can find many copies of this graph in the quasi-random graph. Okay, so now I can tell you how the proof goes in a very, very rough terms. So, the first thing that is done is to use the greedy random method to find a collection of edge disjoint triangles whose union. So remember, we have the whole graph. Let me draw this picture.
So we have the whole graph. And here somewhere, there is a collection of triangles. There is collection of triangles, and there are the edges belong to these triangles. And these are the triangles which correspond to triples x, y, and z, so that x plus y plus z is equal to 0. This is all with respect to some, random embedding of the vertices into side. Okay, now he looked at this side, and he used the greedy random method to cover the edges by triangles. So he covered all the edges by edges-joined triangles. So what he can do is to use the method, and he cover everything except a small number of them. So this is the leftover. So this is the first thing, and what he get in this covering, this will be kept in the final covering. Okay, now there are some leftover vertices which are not in. This is G star, and this is G minus G star. And now for the leftover vertices, he can consider triangles of this kind. So there are no, sorry, not of this kind, but of this kind. So it's one edge which is here, and it's connected to another edge where these two edges are already in G star. And then the next step is to cover this L, these leftover vertices, by triangles of this kind. Again, this is possible with high probability because of all the quasi-randomness properties. And now, okay, now this part is fixed, but this part is tentative, and this guy is something which he will backtrack and re-backtrack until until he can finish the construction. So here now, after he finished with these edges, he used some of the edges in G star. And okay, I think. Okay, I think. So I think now what, okay, so in very rough terms, he wants to find two triangle decomposition of the part in G star, which will allow him to, which will combine together. It will allow him to make the cancellation and get a perfect decomposition of the entire graph. And the reason, so somehow the wiggle room he has is this part, G star, this part is very small fraction of the whole nibble. But so somehow he has to his disposal an application of the greedy random method on a much larger space, and this allows him to enforce precisely some condition on this small space. So I don't know if I can say much more about it. You get, but essentially, using this algebraic structure and using the idea of the semi-random method, it allows to give a precise decomposition. Essentially, you need to use this shuffle, this collection. You can use this. You have many copies of this shuffle which allow you to replace one collection of triangles by another collection of triangles, and this allows you to correct your initial
decomposition and reach a perfect decomposition of the graph. So I think I will not get more into the details. They are not terribly difficult. The general case includes some further complications, and it's considerably harder. But eventually, I hope this gives you at least some taste of the idea. So I want to finish by saying a few things, a few more general things. There is a entire different regime, which is the regime that Q is not constant, and this includes the famous question of the existence of finite projective planes. So finite projective planes are designs of the form Q2 or NQ21, and these designs were so NQ21 or NQ plus 1 to 1, where n is q squared plus q plus 1, and of course we don't know if finite projective planes exist for values of q which are not prime power, and this is a famous question in mathematics. And this is also a question of, and this type of techniques, as far as we know, they are not usable. So we need that the number of blocks is, the number of elements in blocks is constant, or at least growing very slow. Let me end up by proving a theorem that actually Fisher and Erdös de Bruin proved independently in the beginning, in the first half of the 20th century. It's very easy. It says that every design, and now we talk about designs where every pairs of elements is included in lambda blocks of size q. So every design has at least as many blocks as the size of the ground state. So this is a statement where the probabilistic heuristic is completely blind to it, but it has a very nice linear algebra proof. So let me show you the proof. So we have a design, we have a collection of sets of size q, and every pair of elements belong to the same number of them. So now we look at a matrix which is, and we want to show that the number of blocks is at least the number of elements. We look at the matrix, which is the incident matrix of blocks and elements. So we have an n times b matrix, where the entry is 1 if the block contains the element and 0 otherwise. And the claim is that the rows of this matrix, no, this is the columns. Okay, the columns of this matrix are linearly independent, those which correspond to the blocks. And the argument is the following. Suppose we have a linear combination, sum of alpha I vi, which is 0. We look at the inner product, sum of alpha I vi with itself, and this is equal to x times the number of alpha i's square. X is the number of blocks which contain a given element, and times y, or y is actually lambda, times the sum of alpha j for I different than j. So there are precisely lambda blocks which contain the elements I and j. This is the definition of a design. So we will get here this expression. Here y is lambda. And then we can just write it in a different way as x minus y times the sum of alpha I squared plus y times the sum over all I of alpha I squared. And this expression vanish only if all the alpha i's vanish. So this tells you that the projective planes are extremal. You can have a design of parameters n, q plus 1, 2, and 1, or Steiner system of parameters n, q plus 1, 2. So this Steiner system is a projective plane. This can happen only if n is greater or equal to q squared plus q plus 1. And the case where n is equal to q squared plus q plus 1 is the case of projective planes. And as I said, it's a famous question. whether projective planes exist for orders which are not prime powers, whether projective planes for order which are primes, it is a famous question if there are projective planes which are not isomorphic to the Desarguian projective planes, those coming from finite fields. And so I think this is left to a different lecture. Okay, thank you.
Does one know explicitly one design with R bigger than 5?
No.
And in a similar vein, does one know what is the N0? If I give you Q and R, can you give an estimate explicit for this N0?
So I think it's not, I think the proof may give some estimates which may not be terribly large. Mm-hmm. So yeah, I think the kind of techniques, usually they don't lead to frightening high numbers like Ackermann functions or something like that. So it may be something sensible, but I don't know if this was carried out, this computation.